Okay. So can you just have a look at this one for a second, number 3. So first thing is define density.
This is problem.
Okay, what is the definition here? Look up. What is the definition of density?
How much substance or heat?
Now make it a bit more like a formula.
Rho equals m over vol.
Density is mass per unit volume. So as a formula, it's m over v. And what's the unit? Come on, what's the unit? Kilogram per meter cubed. And that's 1 mark, okay? Did you write that down? Avenue?
No.
But seriously, Joseph, why were you late?
I was late for the first class, and well, you don't accept late.
Yeah, but it's you, Joseph. I'd always accept you.
Wait, seriously?
No.
You never should have finished that English class.
Yes.
You could have lived your life.
Yes. Now you know the truth. Okay, next one now. There's a block. Can you make note of these numbers? 30 by 5 by 4. And it's 70% copper and 30% zinc. So I want 30 by 5 by 4, just to make note of that. No, but I want to change these into meters and then do it.
Into -3, -6.
Oh yeah, it'd be -6, yeah.
That's 6 times 10 to the -4.
Okay, so this is A, this is B. So what did you get for the volume?
6 times 10 to the -4.
Okay, meters cubed. Great. Now, it's 70% copper and 30% zinc by volume. By volume. So what I'll do is, we'll multiply this by 70%, and then we'll multiply it by 30%. And this is the copper.
4.2.
Wait, hold on, and this is the zinc. So what did you get first?
4.2 times 10 to the -4.
And the other one is 1.8.
1.26.
Huh?
1.8
This is 1.8.
Oh, right, yeah.
times
I multiplied this one.
Is that right?
8.
Yeah. No, 8.
This is 8.
No, this
Oh.
one's right. One on the left was right.
Back in time. Start again. Right.
4.2
Yep.
times 10 to the -4.
Yep.
1.8
Yep.
times 10 to the
Okay. Fantastic. Now, what is the volume? Oh, we've actually... What?
Yeah, it's 4.8.
Yeah, so that's 1.8.
So when you switch it?
Give me a calculator.
No, you are right.
This is right.
Yes.
Are you sure? Avenue?
Yes, better.
Now, part A. Look up. What is the volume? Done it. There it is there. That's the volume of the block. What is the mass, the copper, and now what is the mass, the zinc? Okay, not quite, that's the volumes. So remember, what does density equal? Mass over volume. So what does mass equal? Density multiply volume. So the mass of the copper will equal the density of copper, which is given as 8.93 times 10 to the 3. 8.93 times 10 to the 3 times 4.2 times 10 to the -4. That's the mass of copper.
3.7506.
Okay, and now the mass of the zinc. So mass is density, and the density is 7.14 times 10 to the 3 times 1.8 times 10 to the -4. So what's that one, please?
1.85.
Yeah. I know, it's amazing, huh?
Yeah.
But no curdy.
That's dangerous.
Don't touch each other.
Yeah.
Slowly.
Yeah, boys, no touching each other. Always good advice. No touching each other, no touching yourself. Good advice. Right? Okay, next part now. What is the density of the total block?
Would it just be the sum?
Yeah, well, the density is the total mass divided by the total volume, which is up the top there, 6 times 10 to the minus 4. So what's that?
8400.
Kilograms per meter cubed. The mass is used to make a long wire of diameter 0.84. What is the length of this wire? Okay. So, what was the, let me, whoop. Okay, what was the mass of this total block? It was, you add the two together, so what's that? What's that there, please? Add these two together. What was the total mass?
4.9. Sorry, 5.0.
5.04. And what was the total volume?
6 times 10 minus 4.
So what you need to picture now is you take this, you melt it down, and you turn it into a long wire. So it changes into, from that into this here. Now, in both situations, the mass will be the same, right? I mean, you're not losing any mass, okay? And in fact, as long as you keep the density the same, that you don't dilute it or mix it with anything else, the volume will also be the same. They give us the diameter here. The diameter, I think we said, was 0.84. So that's 0.42 millimeters is the radius. And they want the length. So any ideas about how I could find the length? How much length I could make? Well, remember I said the volumes need to be the same. So what's the volume of this shape here? What's the formula for it?
Pi r squared L.
Pi r squared L must equal 6 times 10 to the minus 4. So you can get L equals 6 times 10 to the minus 4 all over pi r squared. So I'm expecting this to be pretty long, a couple of meters maybe. What did you get? Can you tell me? What's wrong, Hadil? 0.42, sorry, 42. Abanub?
What?
Joseph?
Yeah, but what did you get?
Joseph, what did you get?
1082.68.
1083 then. That's actually over a kilometer of wire you can make from this block of copper zinc. Is that okay? Yeah. The wire, you put a force onto the wire. So here's the graph. Here's the force and here's the length. That's the length and that's the force. So if you increase the force, you increase the length. Actually, I don't think this is the same wire. No, it's a different one. It just says a length of wire. Anyways, first part, you don't even need this graph. What is stress and what is strain? Okay, so stress, what's the formula for stress? Yeah, so it's just as words. Force per Guys, please. I do enjoy doing physics, but I would like some involvement. So stress is force per unit area. But just to be a bit more precise, we say it's per cross-sectional unit area. And the word cross-section always means kind of the edge that you put the force on. So like here, for this box here, I would say this is the cross-section area. That's different to the total area. Cross-section area is just for one side. Okay, and then what's strain?
That change in the length.
Yeah, the extension per unit original or natural length. Yes?
Yes.
Okay. Now, use that graph to get Young's modulus. Okay. So can I do the second part now? So they want us now to calculate Young's modulus. So Young's modulus is stress over strain, which is force over area over length over extension.
It's extension. The strain.
Sorry, the other way around, sorry. Extension over length here. I'll just clean this up a little bit. I'll write F over extension multiplied L over A. Yeah. Yeah. It looks a bit weird, but what I did was, yeah. Okay. Now, on that graph, what was the two variables? Well, it was force and length. So length is the y and force is the x. So we should rewrite it like that. Length is the y and force is the x. Yeah? So we have Young's modulus equals, well, is that right? Multiply the top by A. There's an A here. Multiply the top by, yeah, okay. So I'll bring the A and the delta L up to the left, and I keep the F and the L here. Now I don't know if they said, is that length or is that extension? Let's see. The length of wire and then the force.
It should have to like form y equal to x plus c.
It should, but I can't get it like that because it's like the y and the x are multiplied here. I do wonder if they meant to say something else, the extension, I don't know. Oh, well actually, hang on. That length there, sorry, that's not the L. The L, remember, is the natural length. It's the beginning length. In fact, this length here is the total length. And what's the formula for the total length is L plus delta L. So we have to do a bit of rearranging here. Let me see. Divide both sides by L. Now, on the graph, y equals F and x equals L plus delta L. Now, how on earth am I going to get that into that?
We could add delta L on both sides without, like,
yeah,
instead of dividing.
Could, suppose. Maybe I'm looking at this the wrong way around. Maybe then trying to go from here to the graph, I should go from the graph and see what I get, okay? So on this graph, this one here is L plus delta L, and this one here is the F. So the slope I can say is that one over that one there. Slope equals L plus delta L over F. Actually, you know something? I'm making this much more difficult than it is. I'm just going to take some values off the graph here. I actually know what the L is. If the force is 0, will the wire be extended? No. So actually, if I just look at this graph really closely, you see this number here? This is the L. Okay? So can you make note here? L equals 3.2964. Can you write that down? L equals 3.2964. Okay? Now let's go to the very end. So at the very end, the length is 3.2988. Can you write that down? 3.2988. Now please take them away from each other and you can give me the extension. So what's the delta L here?
0.0024.
What is it? 0.24.
0024.
And what was the original length I gave you?
Like the first length?
Yeah.
3.2964.
2.3964. Good. Now what else do we need? We need a force. So the force here is 200 at the end. So write down F equals 200. Now, do I have enough information now to get Young's modulus? Almost. I'll have to take one other point. So Young's modulus is stress. What's the stress here? That's the force over the area divided by the delta L. So can you please do this number divided by this number?
Wait, delta L over L.
Yeah.
1.00 times 10 to the minus 3.
1.00 times 10 to the
Minus 3.
minus 3. Good. Now, how many unknowns are in this equation? 2. What's wrong?
It's 3.296.
Yeah, that's wrong.
What's the number here?
Is that the right number? Or
I don't know. You told me. I asked you to write it down.
0.001.
I'm trying. Let's
Oh, L is 3.296, not 2.3.
Yeah, so
Which-
yeah.
Okay, yeah. That should be 3.
Yeah.
Yeah, it's 3.
Sorry, the confusion is somebody gave me the wrong L. What's the length I gave you?
3.2964.
2964. Okay.
Yeah.
Now, here in the denominator, please do delta L over L now. Yes.
0.000.
No, don't give it to me as a power.
Oh, okay. So
Then here.
7.2928 times 10 to the minus 4.
Yes? Now, how many unknowns are in this? 2. So we just need to take one other point on the graph. So I think I'll take the one right here at the 100 mark. So can you write down this length here? 3.2976. 3.2976. Okay, so if I repeat this, I get Young's modulus equals 100 over A. Now what's the delta, what's the original length? That's still the same, 3.2964. And then it's going to be, what number did I just give you to write down?
So 3.2.
Yeah, and then did you do minus that 3.294 so you can give me the extension?
3.6 times 10 to the minus 3.
3.6
6.
times
10 to the minus
for the whole thing here. Okay, 3.6 times 10 to the minus 3. Now that's enough. You have 2 equations and you have 2 unknowns. So if you just write these 2 down, we'll type them into derive and solve them. Did you write them down?
It's 10 to the minus 4.
Oh, for goodness sake. Right, did you write them down?
What did you get?
It should be roughly, it shouldn't be too different from the other one. Alright, did you write them down? Yes? Okay.
It's kind of doubled.
Yes. Alright, read out the first equation, please.
The 200 over A.
Yeah, Young's modulus equals
200 over A
200 over A.
over
Yeah.
7.28 times 10 to the minus 4.
Okay, and the second equation?
100 over A
Yeah.
over 3.6 times 10 to the minus 4.
So, solving those two like linear elimination. Oh, stupid derive. Okay. No good. It says there's no answer to these two. That's not cool. Don't know. I'll have to look at the marking scheme. What? This is number 3, so it'll be around about here. Yep. So I'd be really annoyed if they give me the area as well. Now look.
Possible for A to be equal to 1.
Can you listen, please? Listen for a moment, please. I got 2 equations. Do you remember this? Something similar happened last week. I got 2 equations, but when I tried to solve them, I didn't get an answer. That means I was missing one piece of information. Now, if you look at the marking scheme, they get the L from the graph, right? That's what I did. And they took a pair of points, right? That's what I did. But the one extra piece of information that's in the marking scheme, which I can't see how they got, is they have the area. Now that's not the area from the previous part or anything, is it? What was the area from the last part with it?
5.5.
Yeah, it's different. So can anybody possibly see how they got this area here? Because I can't solve it without this area. I tried to and I can't. I need to know the area. And I don't see it in the question here.
It's okay.
No, it's somewhere in the question here. (2.22 times 10 to the minus 6).
It says a length of the wire, referring to what wire?
Yeah, it's like it's the wire from the previous one, isn't it? But that area is different. Is no.
Well, if you go back and see where the number is. Yeah, you guys said 0.42, didn't you?
The radius.
This is for the radius.
Alright, problem solved. Can you look here? I'll show you something. English thing here. It says a length of the wire. Okay? And actually that changes everything because the word the, definite article, means it's the wire from the previous question also. And you know the radius of this wire. It was given, we worked it out here. So that actually means we know the area. So I can go back now to this. So the answer would be 100 over the area, which is pi or squared. 0. What was it, the radius? 442 times 10 to the minus 3 all over 3.6 times 10 to the minus 4. Sorry about squeezing that in there. Can you type that in, please?
No, I don't.
No, time.
Come on, Avenue, don't just sit there.
The
Type.
timing is whole 2 hours.
Wow, we did 2 hours of physics in an hour and a half. That must be some kind of record. Stupid time dilation. What's the answer?
I think 64961.
Say that again, Ali?
64961.20.
Okay. Did you get that as well, Sam? So the key word here,
The.
unfortunately.
You have to learn English and physics.
Keep an eye, I'd say keep an eye out for indefinite and definite articles in the question. So if there's a definite article, it would mean it carries from the previous part. Yeah. Sayun, in Korean there's no definite or indefinite article, right? Do you have da and a in Korean? I don't think so. Yeah,
Da.
the. It's not in Korean language, right? Yeah. In English here,
Because you
So when I write down anything, I always forget it.
yeah. If you look here in the question,
That answer is not possible.
hold on, Brendan. Sorry.
Sorry?
Joseph.
You should
We're
go
really
with
gonna go through that again.
You see here where it says a length of the wire. The definite article is telling us that it's the same wire as in part previous, which means we can know the area. Now, what's wrong, Joseph?
The answer
Yeah, you know what? He's Brendan now, so I'll
is
be
4.96 times 10 to the 11.
This here, you're saying is not this answer here?
Yeah.
But saying you said you got this answer, didn't you? Yeah. Exactly this also.
Look at it. If that minus 4 goes up, it becomes times power 4.
And this is a minus 6.
6
Shall be minus 2.
minus 10 in total. So how can it? So it would be
No, it
times 10
wouldn't
to
be.
the 10.
No.
Maybe you should have calculated it, Joseph.
I just did.
It's here is minus 6.
Okay.
Then minus 4. That's minus 2.
Okay.
But you're right, these numbers do look quite small, but this should go into that many times. You're checking, Brendan?
Yeah.
You know, the 100 minus.
Do you have the 100? Up the top?
No, it's more.
The 100 is there.
34961.2066. What is that?
Joseph,
I have no idea.
Wait, what?
Hold on. Teacher will sort it out.
No, not that.
No.
Singing.
Yeah,
No,
it's-
someone's.
I think it's an ice cream.
No, children.
What kind of
Children.
Sings an aria.
Focus, please.
You scream!
Ice No, my sister.
I have bad news. Hey, I have bad news. Joseph's right. Yes. You typed it in wrong in your calculator. Yeah, I
Take
know.
care of them, they're
Or is
dangerous.
it supposed to be a really, really big number?
It's usually pretty large.
That's what I got the
What?
first time. 5.01248. No.
Times 10 to the 11th. Okay.
So how is this like?
No, I suspect it's the order in which you get the fractions up on the screen. So if you look here, Brendan, you must create this fraction first. All right, we'll deal with it later.
Brackets.
100 over
Brackets.
Oh, the brackets.
Okay, they wanted now to draw a sketch where you have draw a sketch to show how the extension depends on the force, tensile force applied. In other words, like what I did a moment ago, you want to do a sketch of the force and the extension. So if you remember, here is the force and here's the extension. Or did I have it the other way around when I did it before? Yeah, it was the other way around. Force here, extension here. So when there's no extension, there's no force. Avenue. Would you like me to get Lorraine for you?
No, just
No,
listen.
she told us yesterday she gave up.
On Avenue? No, she didn't.
Did she really
She
say
chased
that?
after him before the start of this class to give him a talking
The
to.
story for today.
Ouch.
Yeah.
I asked Ali if there's anyone like
Hey,
like,
and let me tell you something. Lorraine never gives up. Right, when there's no extension, there's no force. And then as you increase the... No, please. Focus here. When you increase the extension, you get more force. But then if you increase it too much, what happens? It breaks and then it goes like this. So what was the name of this point here?
Deformation.
No, the point is called the elastic limit. And this is called the elastic region, and this is called the deformation region. Yes, yes. You missed this at the start, Joseph. I don't know if you've seen this before. But when you stretch an elastic material too much, it loses its elastic properties. So the graph then no longer becomes linear. Right, which is the end of that part.
Yay.
Yes, indeed. Let's
Break?
check. Hang on, please. We got something close. We got about 5 times 10 to the 11.
5.1. Yeah, it's the same thing.
Yeah, well, it depends how well you read the graph. So that's right. And then the graph, did we show the elastic region? Yes. Did we show the plastic deformation? Yes. Did we show the limit? Yes. And did we do a graph?
Wait, limit
Yes.
of proportionality.
Oh, just the fact that you have the elastic limit where it's limit of proportionality means elastic limit,
Oh.
where it stops being proportional.
Oh, okay.
Yes, yes.
They just worded it differently.
Yes, that's all.
Break?
Hold on.
That's really good.
I tell you what I'll do. How much? Okay. Okay, because 4 is ideal gas law, we'll just go through it quick and then we'll take a break, okay?